Hello everyone and welcome to Digital System and FPGA tutorials. In this FPGA Verilog and Vivado tutorial, we explain how to load data from files into a Verilog and Vivado simulation. Motivation. The standard practice when developing and implementing FPGA algorithms is to first implement and test algorithms in MATLAB and Python. Some people also use C or C++ programming languages for this purpose. This is done since it is significantly easier to test algorithms in MATLAB or Python than in FPGAs. After MATLAB or Python simulations convince us that algorithms work as expected, the next stage is to implement them in Verilog and to simulate them in the Vivado development environment. The final stage is the FPGA implementation. During testing and simulation in Verilog and Vivado, it's often necessary to load a test data sequence that is identical to the test data sequence which is used for algorithm simulation in Python and MATLAB. Consequently, we need to know how to load data from external files into a Verilog and Vivado simulation. The material presented in this tutorial is very important for simulating algorithms implemented in Verilog. In order to demonstrate how to load the data sequence inside of Verilog and Vivado, we consider a simple test case. Namely, we will design a simple Verilog program that will perform bitwise complement of the provided sequence of 2-bit binary numbers. And here's the module that we will implement. It will have two ports, input data and the output data. Input data is the input port, it is a 2-bit binary number, and the output data is the output port, which again is a 2-bit binary number. And we are going to use a simple assign statement to invert the bits of the input data. Over here you can see the timing diagram. In this row you can see the input data. And in the second row you can see the output data. As you can see, the output data is inverted compared to the input data. To do that, we are going to design a simulation test bench, and inside of this simulation test bench we will load a sequence from a file. We will generate 10 2-bit binary numbers shown over here. Then in our Verilog test bench we will load them and we will simulate this program. Okay, let's start from scratch. The first step is to open Vivado. As you can see over here, in my case I'm using Vivado 2024.1. However, you can use any other version of Vivado. Either a newer one or an older version. It really doesn't matter. The principle is the same. Let's create a new project. Click on Next, click on Next, click on Next, and over here you actually don't need to select the board. However, in any case, I will select the board that I really like. Nexus A7. This is the board that I'm using in my tutorials. Click on Next and click on Finish. The first step is to implement our Verilog program, that is to define our module. To do that, click here on Design Sources, then click on this sign, click on Add or Create Design Sources, click on Next, and over here create File. Let's call the file simply as Test Module. And let's click on OK. Click on Finish, click OK, and Yes. And after some time, if you expand this folder, you will see the test module. Double click on the test module, expand this window, and let's start with coding. First of all, I will erase these comments. Then, let's define the ports. We will have two ports. The first one will be input data, and the second one will be output data. Here it is. Let's make that everything looks good and add a semicolon. So we need to declare them. The input port will be a 2-bit port, and its name is input data. Similarly, the output port is again a 2-bit port, and it's called output data. And that's it. Now let's write a simple equation that will invert the bits. So we use the assign statement, and we simply say output data is equal to complement or not of input data. And that's it. We end the semicolon, and let's save our module by pressing Ctrl S. Good. The next step is to create our simulation module. Let's expand this sources menu over here, and let's click on simulation sources, and over here click on plus. Make sure that add or create simulation sources is selected, click on next, and click here on create file, and let's call the file simply as simulation. And click on OK, click on finish, and click OK again, and yes. And here it is. Let's expand this part over here and double click on simulation. Again, let's erase these comments, and let's start creating our simulation test bench. First of all, we don't need the parentheses over here. The main purpose of this simulation file is to load a binary sequence from an external data file and to send this sequence sample by sample to our FPGA design. Consequently, before we continue with the implementation of this simulation file, let's create our data file. For that purpose, create a folder. In my case, the folder is located in codes and it's called FPGA test. And inside of this folder, create a data file. You can use any editor. In my case, I'm going to use Notepad. So do the right click, click on New, and find a Notepad or create a simple text document. I will call it as input.data. Here it is. And let's open this file and let's define our sequence. The sequence will look like this. It will be 0, 0, and before I explain this, let's go back again and let's see our module. We can see that over here the input data is a 2-bit binary number. Consequently, over here you need to define a sequence of 2-bit binary numbers. That's why I start with 0, 0, then let's do 0, 1, let's do 1, 0, 1, 1, then let's repeat 0, 0, 0, 1, 1, 0, 1, 1, and let's add, for example, 2 additional numbers, 0, 0, and 1, 1. Let's save this file and let's continue. Next, we need to add this file to our project such that Verilog and Vivado know how to reach this file once we refer it inside of this module. To do that, click on Design Sources, then over here click on plus, click on Add or Create Design Sources, then click on Next, click on Add Files, and locate that file. Over here, you need to find the path to your file. In my case, it's codes FPGA test, and you will not see the file. Why is that? This is because you need to change the files of type. So let's click here and let's go all the way up and let's click all files. And once you do that, you'll see the file, click on the file, click OK, and click on Finish. And after some time, you will see Data Files folder over here, and you can see our file. Similarly, inside of Simulation Sources, you will see the data file over here. Good. We can continue. Let's go back to our simulation and let's continue with implementation. Let us start with declarations. First of all, we need to declare an integer variable that will iterate through the rows of our data file. I will call this variable simply as k. Then we need to declare our input data and output data. The input data will be a register. It's a 2-bit register, and I will call it simply as input data. Then I need a wire for the output. Consequently, I will type wire. It's a 2-bit binary number, and I will call it as output data. Next, I need a register for my clock. The clock will be used to simulate the circuit, and you will see it later on. Next, we need to define our clock. So how to do that? I like to do it like this. I like to use an always statement, and then I'm usually specifying the period of the clock, or better to say half of the period of the clock. In my case, the half of the period will be 10. And what's the unit over here? If you go back at the top of the file, you can see that the unit is 1 nanosecond. Consequently, half of the period of the clock will be 10 nanoseconds. And then I simply need to write clock is equal to inverted previous version of clock. And that's it. Next, we need to declare an array that will store the data from our file. But let's go back to the file. Open the file and let's count how many rows this file has. It has 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 rows. Good. So we need an array with 10 entries. Every entry inside of this array will be a 2-bit number. To declare this array, we need to again use registers. Then we need to specify the bit width. And over here we need to give the name to our array. I will call it simply as data. And data will have 10 entries. And that's it. Okay. Next, we need to declare and define our module under test. To do that, we need to go to our original module. We need to copy the module name, paste it over here, and then we need to give the name to our unit under test. I will call it simply as UUT. And inside, we need to define the connections. That is, we need to connect these variables over here with the ports of our module. Consequently, we copy input data over here, then we type dot input data. This variable is actually the port from our module, and you know that it's a port since it starts with a dot. And then over here we need to define the connection. This input data variable should be connected with the input data inside of our simulation. Good. Then let's add comma, and let's do the same thing for the output data port. Copy the output data port, go over here, type dot, output data, and connect it with the output data. Good. And that's it. Next, we need to define our simulation. For that purpose, we need to type initial, then after that begin, and let's close initial begin. We do that by typing end at the end. Okay, so first of all, let's initialize our clock. We set it to 0 initially. Then let's initialize our counter k. To remind you, k is an integer declared over here. And over here, we need to read the data from the file. Read the data from the file. How to do that? To do that, we need to use this statement. We start the statement with a $sign, and we need to type read, and then we need to type MEMB. This stands for read member. We need to specify the name of the file. The name of the file is input.data. This is our data file, and you can see that the data file is included in the project, and we need to specify where we are going to store the data from this file. We are going to store it inside of this array or register called data. So comma data, and then don't forget the semicolon. So what will happen over here? We are going to read all the rows of our input.data file, and we will store it inside of this array. Okay, after we do that, let's introduce a small delay. For example, let's do 20 nanoseconds. And over here, let's start a for loop that will be used to read the data. So we've typed for k is equal to 0, then k is smaller than 10. Why is that? Because we have 10 rows inside of our file, and the rows start from 0. Then over here we need to increment k. We simply type k is equal to k plus 1. Then after that we type begin and end. In this way we are actually closing the for statement. Inside of the body of the for statement we need to type this at, and then over here pos edge, which stands for the positive edge. Let's type it correctly like this, pos edge clock, and then semicolon. So what will happen over here? We will start the execution of this for loop. Then over here we are waiting until a positive edge of clock arrives. Positive edge is a rising edge of the clock, and we are not going to proceed until a positive edge is detected. Okay, and after that what do? We simply do this. Where is our input data? Here it is. Input data is actually connected to this port inside of our module. So we need to type this input data, and then we are going to store inside of input data a corresponding row from our data file. We will write data and then the index k, and that's it. Simple as that. So again, this for loop will start and it will iterate for increasing values of k. Inside of the body of the for loop, we are waiting for the positive edge of the clock. Once the positive or the rising edge of the clock arrives, we read the data, or better to say the data is already read from the file. We simply take the data from the data array and we feed it inside of the input data port of our module. Then the module will invert the bits, or it will compute the complement of the bits, and over here in the simulation time diagram we are going to display the result. The result will be output data. So let's run the simulation. Save the simulation. Then over here find this option run simulation, click on run simulation, and then click on run behavioral simulation, and let's see what will happen. Now wait here, and voila, here it is. Let's expand this window, expand it over here, and let's see what's happening inside. Okay, to zoom out the simulation window, press and hold Ctrl and use the middle mouse button, that is the roller on your mouse, and zoom out until you see clocks over here. So let's see. First of all, clock is initialized at 0. That's precisely what is written over here. Then we start. We see that the clock is accurately being switched. Let's see the period. The period is obviously 10 nanoseconds. So that's correct. So clock works as expected. Let's see our index k. Here it is. Okay, so if we increase the slider over here, we can see how k increases. 1, then we can see further 2, 3, 4, 5, etc. It goes until 9. This is also good. Let's check the input data. What do we see over here for the input data? Well, for the input data, we obviously see integers, right? This is because Verilog, or better to say Vivado, automatically converts the binary number inside of the integer value. However, we don't want that. We want to see the binary numbers. To do that, click over here on the input data, or better to say do the right click, click on radix and find binary. And now you can see the input data in the binary form. Let's do the same thing for the output data. Click here, do the right click, radix and binary. Here. First, let's double check that our data is properly loaded. Over here you can see the input file, and in this row you can see the input data that's being loaded. We can see 0, 0, 0, 1, 1, 0, then we repeat the sequence, and then we have 0, 0, and 1, 1. So if you now move the simulation, you can see that everything is okay. 0, 0, 0, 1, 1, 0, 1, 1. Then this sequence is repeated again, and then finally we have the last value over here. Perfect. Next, let's make sure that everything is being inverted as expected. To do that, we will just compare input and output data. We can see that over here we have properly inverted everything, since originally we had 0, 0, and the complement of 0, 0 or negation is 1, 1. Then we have 0, 1, 1, 0, etc. This means that everything works as expected. Okay, that's all for today, and thanks for watching.